Hello everyone, welcome to Sweetie Speaks official YouTube channel. Today's topic is pipelining hazards. This is computer architecture series, and in case you missed the video lecture on pipelining in this series, please go through that first and then come back here to understand the pipelining hazards. Let's get started. What do you mean by pipelining hazard? Pipelining hazard is necessarily a dependency which will prevent your instruction from executing in the designated clock cycle. I have highlighted the keywords dependency that prevents the instruction from executing in the designated clock cycle is pipelining hazard. There can be three types of dependencies, or we call it as hazard. The first one is structural dependency. Structural dependency is due to the hardware resources. There is a possibility that in the same clock cycle, two different instructions in your pipeline want access to the same resource. Say a particular register. Two instructions in your pipeline need access to register at the same time. This kind of hazard is called as structural hazard. The second hazard is control hazard. Control hazard happens due to branch instructions. What happens in the branch instruction? Your control jumps to some other instruction. In this case, your control hazard will occur because suddenly, due to some branch instruction, your program control is moving to some other location, not the next instruction. That is why the control hazard occurs. Data hazard occurs when the data in the first instruction is being used in the second instruction. Let me give you an example. Say in the first instruction, I am writing a value to register R0. And in the second instruction, my R0 is being used as an operand. It means I want to read the value in R0. Now, until your first instruction does not complete execution, it does not complete write back, your data is not actually written into the register. So if second instruction wants to access that register in the same clock cycle, if when your when your first instruction is in instruction fetch, then your second instruction is not in pipeline yet. But when your first instruction reaches instruction decode, your second instruction is in instruction fetch. Then when your first instruction is execute, the second instruction is in the instruction decode stage. Now while decoding, it knows that it needs access to R0. But the problem is if it goes and reads the value of R0 during execute, then it will get the old value because when your second instruction is in execute, the first instruction is not yet completed. It's not yet in write back, so you will get the old value. This kind of hazard is called as data hazard. There can be multiple solutions for hazards. The simplest solution is to introduce stall cycles until your dependency is resolved. What is the problem in introducing stall cycle? Stall cycle is like wait cycle. Until your dependency is not resolved, you introduce wait cycle. It means your instruction will wait. Due to your instruction waiting, the next instructions will also wait. And say that there is a instruction in the next instruction which also has hazard, then again a lot of wait cycles will get introduced. This way your CPU performance will be drastically impacted, which is the biggest disadvantages of introducing stall cycles. That's why it's not an ideal solution. We'll see what are different type of hazards in detail and what are different type of solutions for that hazards and what are examples. Let's see. The first one was structural hazard. As we said, it occurs due to hardware resource conflict. What are different hardware resource? It can be memory, it can be register, it can be CPU. Structural hazard occurs when more than one instruction in your pipeline requires access to the same resource in the same clock cycle. Say there are two consecutive instructions which require access to the memory in the same clock cycle. Then you get a structural hazard. What are solutions? First one is to introduce stall cycle. But we saw that introducing stall cycle means you are making the instruction wait till your dependency is resolved. If you do that, then your other instructions will also wait. And finally, your CPU performance will get impacted. That is why it is not an ideal solution. What can be other solution? For structural hazard, one solution can be to increase resources. How can you increase resources? One way is to increase pipeline stages. But if you increase the pipeline stages, it will introduce more complexity to your pipeline. This is one of the disadvantage. Another solution can be, say you were using same instruction and data memory. So the first instruction wanted to access data memory and while the second instruction wanted to access instruction memory, but since both are same, you have a resource conflict. In that case, you can separate out your instruction and data memory. You can introduce multiple levels of cache memory. Now say there is a condition in which your ALU is used for address calculation in one instruction and your ALU is being used to execute an ALU instruction in the other instruction. In such cases, you can resolve the conflict by adding exclusive ALU for your address calculation. In case you have conflict with register, you can introduce registers with multi-port access, wherein at a time multiple instructions can access your registers without any conflict. So depending on your situation, you need to decide what is the best solution which works for you. This is how we can resolve structural hazards. Now let's see data hazards. When does data hazard occur? When instructions execution depends on the result of some previous instruction which is still in pipeline. Say you have one instruction and the result of that instruction will be used by your second instruction. That is when your data hazard occurs. Let us see different types. The different types of data hazards are read after write. What does read after write mean? You are reading the value of say R0 after writing to it. But the problem is your value is not available in R0 till write back stage. But you want to read it in the next instruction. So if you do that, you will get an old value if you don't resolve the hazard. That is the problem. Similarly, we have write after read hazard. Then we have write after write hazard. Now what will happen in write after write hazard? I am writing value to a register and the register is not yet written. The value is not yet written and in the second instruction I am again writing a new value. So this is a write after write hazard. Let's see some examples. We have add instructions and subtract instruction. Let's see. Here what is happening? I am writing value to R0 in the first instruction and in the second instruction I want to read the value of R0 to perform this subtraction operation. But when this is in execute stage, this has not yet completed write back, so the value of R0 is old. That is why it's a data hazard. Similarly, if you see here, you are writing a register after read. Here you are reading R0 and after that you are writing the value of R0. So when this operation here, there is a write after read hazard. Write after write hazard, it means you are writing to a register and in the next instruction you are again writing to the register. This is write after write hazard. How will you resolve it? One solution is stall cycle, but we already discussed that it is not the ideal solution because CPU performance is impacted. The other solution is instruction reordering. You can reorder the instructions in such a way that there are minimal dependencies. If all dependencies can be eliminated, well and good. If not, try to have minimal dependencies. This is one solution. The other solution is data forwarding. What does it mean? See, we will see this example. Here you are writing a value to R0. Now you know the result of R0 in execute itself. It's not written back to the register R0, but you know the result. So when this is in execute, this is in instruction decode. So I will forward the result of this R0 directly to this second instruction so that it gets the latest value of R0, whatever was calculated during execute. Then and there itself, your next instruction will get the value of R0. This is called as data forwarding. The problem with data forwarding is you just need to add some extra logic to identify the hazard and act upon it. But it will give you good results because you don't have to impact the CPU performance. Then again, you don't have to take the pain of reordering instructions. So, data forwarding can be one of the good solutions. Let's see control hazards. We already said control hazards are caused by branch instruction. What happens is decision to execute a instruction is based on the result of another instruction like a conditional branch. Let's see an example. This is the pointer 20 is the program counter value. And here you have the first instruction which is add. The second instruction is jump. The program counter is 201. And the third instruction is subtract. The program counter is 202. But after this instruction, your program counter should directly jump to 210. It should not go to this instruction. So what happens after this instruction is fetched? This instruction is fetched. So when this is in decode, that time you understand that it's a jump instruction. But by that time, this instruction is already fetched. The program counter value is this 202. So this is unnecessary because 202 we don't want the program counter to go here. We want the program counter to go to 210. So this is unnecessary which happened that program counter value became 202. This is a control hazard because your control should have moved after jump, your control should have moved to 210, but the program counter was holding the value of 202. What should we do to solve this? One is introducing stall cycle till your branch instruction is not decoded. Again, not the ideal solution. Other is instruction reordering, wherein you reorder the instructions to avoid such control hazards. The third type of solution is dynamic branch prediction. It means we will predict what will be the branch prediction. How are we going to do that? We will maintain the history record of your all previous instructions which were executed. We will maintain the record of those instructions with the help of branch table buffer. BTP is the branch table buffer. What is BTP? It's like a memory. You can consider it like a cache memory which will have the set of entries with the PC address. PC is program counter address of the branch instruction. What was the program counter of the branch instruction and the corresponding effective branch address? Say first your program counter was 201. After decoding, it went to 210. Such kind of information will be available in your BTP, which is branch table buffer. So next time when you come across this instruction with the program counter 201, you know with the help of this, you know that next you have to move to 210, not to 202. So it will look for a matching branch instruction. Say this one itself, 201 was the program counter and this instruction has come. Then it will see what was the corresponding effective branch address. It went to the program counter 210, not to 202. So it will predict that you have to go to 210 only, not to 202. So instead of fetching 202 program counter, it will fetch 210. This can work if the prediction is correct. Sometimes your prediction may be wrong. When your prediction fails, then you need to flush the value of program counter which came, which was 210. With the help of BTP, we had fetched 210, but say the prediction has failed. There was some other instruction, and that other, according to that other branch instruction, you have to execute the next instruction. So the value of 210, which was picked as the program counter, will be flushed, and 202 will be the next value picked. So this causes some latency. But most of the times branch prediction works. Rarely this will be the case. So dynamic branch prediction in the real life scenario, it is a very good solution for control hazards. I hope with this the pipelining hazards are clear. What are different types? What are the examples of it? What are different solutions for it? To stay tuned to such content on DLSI, please subscribe to Sweetie Speaks official YouTube channel. Thank you.